Hello, quantitative methods, and welcome to our module on null hypothesis significance testing. This is probably the most important module in the entire course, and this is a series of lectures that I think you're going to come back to time and time again as we go into more and more complicated statistics. But this is the basis of how we do all inferential statistics, at least in this course. And talking about null hypothesis significance testing is kind of like telling you how to drive a car. I can talk to you about how to drive a car till I'm blue in the face, but you won't actually know what's going on until you get behind the driver's wheel and take the car for a spin yourself. So I'm going to talk about null hypothesis significance testing and go into all of the details, and hopefully you'll get the majority of what I'm talking about. But it probably won't be until after we talk about a few specific instances of inferential statistics before you really get the hang of what's going on. So after you listen to this lecture or series of lectures one time, if you don't understand what's going on, that's not a horrible thing. Just make sure that you might return to this after we've get some more experience under our belts about some specific instances of inferential statistics, like the one sample z-test or one sample t-test. All right, so what we're going to do in this module, we're going to first talk about inferential statistics. What are they all about? And talk about the major problem that we encounter with inferential statistics, a problem that we need to figure out how we're going to solve. Then we're going to talk about the way in which the majority of psychologists think that we should solve this problem of inferential statistics. All right, there are two major approaches from way back in the day of how to solve this problem. And what we did as psychologists, what we did as statisticians, what most scientists do, is they use this kind of Frankenstein monster of these two different approaches. And the kind of name for it is null hypothesis significance testing. It's a combination of an approach by Sir Ronald Fisher, which focuses on p-values, which we'll talk about, and it's also an amalgamation of Neyman and Pearson's idea about hypothesis testing. So we'll go into what those two approaches are and what is the approach that we take nowadays when we are trying to solve problems with inferential statistics. Okay. So first of all, what are inferential statistics what are they all about? So most of the time in psychology, we care about populations. We care about, is this population mean different from this population mean, right? Let's say something about the personality trait of aggression. Is aggression different between men and women? All right, well, we might have a sample of 10 men and 10 women, but that sample mean difference that we have between men and women, it's probably not going to be exactly the same. So what we care about is that in the population, for all men, for all women, is there a difference, not just in that particular sample. When we're doing a drug study, and we have an experimental drug and a placebo, now we might get sample mean differences. Maybe the drug gives slightly less depression or symptoms of depression than the placebo. But what we care about is not just if there's a difference in those sample means, but in the population. If everybody were to take this drug, would it decrease symptoms of depression? So inferential statistics, we are examining data from a sample, and we are inferring about what is happening in the population. All right, everybody that we're interested in. Let's do the following example, at least for a couple slides. Are UNG students better at psychology than UGA students? This is an inferential statistics question. All right, well, what we might do is we might take 10 subjects randomly, use random selection from UNG, and then give them a standardized test of psychology, and then randomly select 10 students at UGA and give them a psychology test. Calculate those two sample means and examine them. All right, let's say that on this standardized psychology test, we see that UNG has a mean of 250 and UGA has a mean of 240. All right, are we convinced at this point in time? Yay, UNG students. All right, we are better at psychology than UGA students. Maybe, right? This could reflect a real difference in the population, but this could just as easily reflect a difference in just random sampling. Maybe it's the case that we selected psychology majors at UNG and we selected non-psychology majors at UGA. Maybe we randomly selected the smarter UNG students and randomly selected the dumb UGA students, okay? How do we know? Is this due to random chance or is this due to a real effect? And no matter what the difference is, if it's a huge difference or if it's a small difference, still might be the case that it's due to random chance. Right? There's always some probability that the findings that we get are just due to sampling error, and that in actuality there is no difference between these two population means. In fact, we could do this again, this exact same thing, and we might find that UNG has a lower sample mean than UGA. All right, you might find this result if indeed UNG is actually better at psychology than UGA in the population. Just due to random chance, we might get the sample means to be flip-flop, where UGA seems to be better. All right, ooh, this is problematic. How are we going to go about and make our decision about this mean difference is so large that we say in the population there is truly a difference? Or maybe this mean difference is so small that it's very likely that we have found these results just due to chance. All right. So let's say that we were to know what truth is. All right. Let's say that truth is the following sampling distributions. So again, these are sampling distributions. These just aren't any old normal probability distribution. These are sampling distributions in which we are randomly sampling 10 UNG students, randomly sampling 10 UGA students, writing down their mean, tossing those 10 students back, and going through the process again and again and again. I showed you the dance last time. That's what we're doing. And we record all those data, and we put them in these graphs. So this is truth. All right, if we were to do this an infinite amount of time, this is truth. Now, when I do this, not via Zoom, I have lovely drawings that I do for my students. So I'm not going to neglect you. So let me show you what's going on here. So for the red, we've got UGA. And so we're going to draw UGA. There we go. Does that look like a dog? Yeah. All right. So that's UGA. And I'll draw, we'll have Nigel here. I guess the mouth is over there, but you know what? I would never want to neglect you and not have you have some of my drawings, so we'll go with that. All right, so blue represents UNG in this case, as represented by Nigel. Lovely drawing of Nigel. And UGA, here we have UGA. All right, this is truth. All right, so maybe it's the case that we do our study and we find, let's do a different color here, that we get maybe some of the dumb UGA students. Okay, and we find a sample mean right around here, like 220. And maybe it's the case that we have, we randomly select UNG students, and we get a fairly high sample mean, all right? And so we might conclude that, you know, this is a pretty sizable difference. Well, that could be the case, but it could equally, well, it could also be the case, let me get rid of these real quick, could also be the case that we get really smart. So I'm going to this red distribution here. We get really smart UGA students, okay? Just do the random chance. And maybe we get relatively dumb UNG students. And here we would come up with the exact opposite conclusion, all right? So this is problematic. These means or these sampling distributions are pretty much overlapping. There is some difference, but there is a decent amount of overlap between the two. It's really hard to tell if there's a difference between the two of them. All right, so we need to be concerned that just due to chance, just due to this random sampling, we might come up with an incorrect conclusion. So how are we ever going to be confident in saying that there is a true population mean difference between two groups, between two conditions? All right, let's jump forward a little bit. So that's one example. Here's another example of a problem from inferential statistics. All right, so maybe the average on Beck's anxiety inventory is at 21. Is the score for dog owners different than the average? All right, we might randomly select dog owners. Maybe it might be 10 of them, might be 30 of them. We might get a score of 18. All right, okay. Is that 18? That's a little bit different than the average. It's lower than the average. But does that constitute as a great enough difference, a large enough difference, that we're going to say that in the population, it's probably the case that dog owners have less anxiety than the national average? All right. Here's my dog, by the way. This is Tara. She is a very good girl. So maybe we have a inferential statistic kind of question like this. All right. Here we might have the population. This is our sampling distribution here for Beck's anxiety inventory. If, let's say, that we have a cutoff, let me get my pen out real quick. If we have a cutoff right here, and if we have scores lower than this cutoff, then we are going to say that there is a true population mean difference. There still is some probability, and again, this is the sampling distribution if there is no effect. There's still a great deal of probability, all the area underneath here, that we make a mistake. All right, that we make a mistake and say that there's truly a difference, when in actuality, there is no difference between owners of a dog and the national average. All right, we need to be mindful of this when we are doing our inferential statistics. So again, the problem we need to be thinking about is, how are we ever going to solve this? How do we determine when is it the case that very much likely there's a high probability that there is a true difference in our groups, between our groups? Or is it the case that the results that we found are probably due to random selection, probably due to error? How do we make that determination? Okay, this is the critical problem of inferential statistics, and that's what I wanted to get you. I wanted you to get from all of this. We can always find a difference in the sample means, but the difference in the sample means could just be due to random chance or error. How do we go about with our decision-making process to determine when the sample means are so large that we infer that there is indeed a difference in the population? All right, how do we end up making those decisions? Okay, how do we deal with this random error or random chance causing some differences in our sample means? How do we account for that? That's the critical problem of inferential statistics. All right, just some other examples of questions that we can use that use inferential statistics. So let's say that we have a new drug, maybe it's something like Prozac, that's supposed to alleviate the symptoms of depression. All right, we need to conduct a research study to see if it reduces the symptoms of depression above and beyond a placebo. Okay, we're inferring things from a sample to a population, very important. Maybe a more cognitive study. Do students learn better, learn a language better from an immersion classroom or from a traditional foreign language class in which you talk a lot about grammar and you talk a lot about rules of the language, as opposed to fully immersing you in the language and don't really talk about the structure that much? All right, we might conduct a study, maybe 30 students in one class, 30 students in another class. How do we go about inferring from those differences among the samples to what's happening in the population? Because again, one class just might be smarter than the other just due to random chance, just due to error. Mean differences aren't the only thing that we care about with inferential statistics. We can do some other things, all right? So maybe we look at a linear relationship, maybe with a correlation. Is there a relationship between the personality trait of agreeableness and the length of one's marriage? Or is this relationship so negligible that we can assume that it is zero in the population? What we might do is we calculate a correlation coefficient for maybe 100 people that are in our study, and we have to infer from whatever that correlation coefficient is. Maybe it's like 0.1, maybe it's 0.2. That is there a statistically significant correlation in the population? Does agreeableness actually predict the length of one's marriage? So we can ask inferential statistics, ask questions about linear relationships with correlations. We can look at variability as well with inferential statistics. Is the variability or the variance of intelligence scores different for males and females? Here we're not talking about population means. We're talking about population variance. So there's many different kinds of inferential statistics out there. So here's an important question. If we have the population parameters, do we need inferential statistics? And the answer is no, we don't need it. If we know what the population means are, we don't need to do any statistics. We can just compare the population means, all right? If the population mean for all UGA students on that psychology test is 100, and for UNG students it's 120, we don't need to do any inferential statistics to say which school does a better job at teaching psychology or what school has smarter students in psychology. We've got the population parameter. We can just compare those two. One's 20 points greater than the other one. All right, we don't need to account for any random variation or random error or random selection because we've got the population parameters. We can compare them with our eyeballs and don't need inferential statistics to do that. All right, hopefully that problem makes sense, all right? P-values. All right, so in the early days of pretty much science, all right, how do you account for this random error? How do we deal with this critical problem of inferential statistics? Well, way back in the day, people just reported means. This mean is bigger than this mean, and I'm going to leave it at that. And they might include the standard deviation or something like that, but they're not coming up with any conclusions or trying to infer what's happening in the population using any inferential statistics. Okay, but in the 1920s and 1930s, there was a very lively debate about how we should do our statistics, our inferential statistics in sciences. And there were two approaches. There's one approach by Sir Ronald Fisher. Sir Ronald Fisher is a very famous statistician. He is also a very famous geneticist. He had very many contributions in the field of evolutionary biology and population genetics as well. Just some of his accomplishments. The p-value that we're going to talk a lot about in this class that SPSS calculates fairly easily, that's all Ronald Fisher. He didn't develop the t-test, but a lot of the applications of the t-test he worked on. The analysis of variance, which pretty much the third section of this class is just ANOVA. Again, that is all Sir Ronald Fisher. He also did, as I mentioned before, some very important genetics research, came up with some important statistics in genetics. He came up with the sexy son hypothesis, which I like the name. That's a kind of a fun name for a hypothesis, but it's the theory that the females of the species select for certain, are attracted to certain males so that their offspring will be more likely to attract females. So why does a female peacock mate with a male peacock that has a bunch of lovely tail feathers? Well, because her son, if she has a son with that male, is likely to attract other females as well. So the sexy son hypothesis. Kind of a fun name, as I mentioned. So Sir Ronald Fisher has done a lot of good stuff in statistics. Some stuff in genetics that's good, but he was a eugenicist and very racist and had a lot of very horrible opinions as well. So we have to be mindful of that. Pretty much any of these statistics, a lot of the individuals in the early 1900s that contributed to statistics had very good ideas about statistics, but had very, very horrible ideas about race. So Carl Pearson, Francis Galton, all these individuals, we base a lot of our statistics off of them, but we don't base a lot of our opinions off of race and genetics off of them because they had some really, really horrible opinions about these things. So I just wanted to be mindful when we talk about these individuals that we talk about everything in their career. All right, so Sir Ronald Fisher had his approach to solving the critical problem of inferential statistics. And there was another approach. This is the approach by Jerzy Neyman and Egon Pearson. Now, Egon Pearson had a famous uncle, and his famous uncle is Carl Pearson. And if you are familiar with correlation coefficients, you know that they are called the Pearson correlation coefficient. And they're actually named after Carl Pearson and not Egon Pearson. Okay, but the two were related to one another. And so there were these two different approaches for how to do inferential statistics. And this was a very, very lively debate. I say lively, but Sir Ronald Fisher and Egon Pearson seemed to hate one another. It was a very, very intense argument with one another about the proper way of doing inferential statistics. They both had their own journals, and they wouldn't let the other one publish in the journals, and it was really contentious. So we're going to talk about Fisher's contributions to this endeavor. We're going to talk about Neyman and Pearson's contributions to inference statistics as well. And as I mentioned, today in modern psychology and modern science, we use an amalgamation of these two approaches. All right, so when I use the term null hypothesis significance testing, when you look at the vast majority of psychology papers today, it is kind of a Frankenstein monster of these two different approaches. Is null hypothesis significance testing the only approach to doing inference statistics? And the answer is no. All right. Statisticians have disliked this way of doing statistics for a long period of time, but no one can agree on an appropriate alternative. So this is kind of the default. It's not the best way, and it has some problems with it, and we'll talk about the problems of null hypothesis significance testing. But it works, and so it's what the majority of psychologists use. It's what the majority of biologists use. So we're going to talk about it because it's pretty much the starting place for everything. If you end up going to graduate school, you might learn some other different approaches, and that's great, but everybody's going to start you with this, all right? So that's what we're going to do. All right, 1 second. All right, so what is Fisher's approach to inferential statistics? Well, he wants us to calculate a p-value. And what's a p-value all about? Well, to explain this, let's talk about Fisher's very famous example of inferential statistics, the lady drinking tea study. All right, so Fisher at a tea party encountered a woman who claimed the following, that she could tell when drinking a tea if the tea was poured in first or if the honey was poured in first, or milk. Okay, sorry, honey, milk, whatever. So she could tell if the milk was poured in first and then the tea, or if the tea was poured in first and then the milk. Now Fisher is probably like, no, you can't. That's dumb. No one can do this. So how do you test if she truly has this ability? All right, well, you could, make a tea and then give it to her and say, okay, which is it? And she tells you, but there's a chance that she's just guessing, right? There's a 50% chance that she gets it right just due to random chance. All right, so maybe you need to change the study in some way. Maybe we give her many different teas, some of them in which we pour the milk in first, some of which we pour the tea in first, and we see how many she gets right. Right? But no matter what we do, there's always some probability that Muriel gets it right just due to chance. At what point in time are we going to make the demarcation that Muriel has some super tasting ability that she knows when the tea was poured in first or if the milk was poured in first, okay? So we could do 2 glasses of tea, but again, there's a 25% chance that she gets it right. Okay, well, Fisher says that what we should do is calculate a p-value. A p-value is the probability of obtaining a result at least as extreme as the observed results. Okay, so let's say that we gave Muriel 10 glasses of tea, all right, and she correctly guesses 9 of those 10. Well, the p-value is the probability, just due to chance, that you would have got 9 right, so that value that she actually got right, and more extreme values, so all 10. Okay, that's what a p-value is. It's a probability of obtaining the observed results and any more extreme results, any more statistically extreme results. In other words, a p-value is the probability that our findings are due to chance and that there is no effect in our study. All right, so let's do the following. Let's say that Muriel receives 3 teacups and she correctly guesses each one of them. How would we calculate the p-value? Well, let's write out all of the potential outcomes. All right, so here the zeros represent Muriel gets none of them right or doesn't get it right, and the x's represent that she gets them correct. Okay, it could be the case that Muriel gets none of them right. All right, there's only one instance that she gets all of them wrong. She could get one of them right, and there's 3 instances that this could happen. She could get the first cup of tea right, the second cup of tea, or the last cup of tea. All right, she could get 2 cups of tea right, and here are the instances that she could get those right, and she could get all 3 of them. All right, and there's only one instance of this. So what's the probability that she gets 3 of them right or a more extreme result? Well, 3 of them right is the most extreme result. So just what's the probability that she gets all 3 of them correct? This is one instance out of all the other potential instances. That's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different choices that Muriel can make. Only one of them gives all 3 correct. So the p-value for this is 1/8. So we have a p-value of 0.125. There's a 12.5% probability that Muriel would have correctly guessed 3. All right. Fisher argues that we should report this p-value when we are doing our inferential statistics. Okay, it's easy enough if we're doing a dumb study about tea and milk. All right, and there's only 2 outcomes and there's only 3 different cups. P-values are going to get very complicated when we're talking about a continuous variable, where it's not just right and wrong, but maybe we're looking at reaction time, which is in milliseconds. Right, when we're looking at many different trials, when we're looking at many different subjects, this p-value calculation is going to get complicated. Let's do one more. All right, so what is the p-value when we have 5 cups and she gets 4 of the cups right? Okay, there are 32 different outcomes. I have written all of these outcomes out here. If you've had elementary statistics, you know about permutations and combinations, and there are formulas to calculate this, but we don't go over that in this class, so I'm just going to do it the old-fashioned way, just list out all of the different instances of Muriel getting this right and wrong. All right, how do we calculate the p-value? So how many instances as extreme as 4 cups right or more extreme? So for 4 cups right, we have 1, 2, 3, 4, 5. More extreme result of this is getting all of them correct. So what's the probability that Muriel gets 4 right, or a greater amount, just due to chance? Well, that's 6 over 32 different outcomes. And so she has a 18.75% chance of getting 4 or more correct when she does this, okay? So that's pretty sizable. All right, and that's how we calculate p-value. Now, we are never going to calculate p-value in our studies. We're going to let the computer calculate it because it's very complicated when we're actually looking at real data. For this example, it's easy to sort of show you how we go about calculating p-value for a discrete variable, where you can be right or wrong, where there's a limited number of outcomes. But when we get into our real data, this p-value calculation is going to get complicated. So Ronald Fisher proposes that for any scientific study, we should calculate and report what the p-value is. and he gives this guidance to people. And this guidance is going to be famous, that, if the p-value is 0.05 or smaller, then we can practically say that we've got a statistically significant finding, that we have a true effect. If the p-value is greater than 0.05, then it might just be due to chance. So he gives kind of a throwaway message that 0.05 might be used as a practical applied cutoff. But it doesn't put too many eggs in that basket. But when we get to psychologists, when we get to people actually using this, they will treat the cutoff value of 0.05 as holy, as the cutoff point. If it is less than this, then we are going to say that there is an effect. If it is greater than that, then we say that there's absolutely no effect. All right, which isn't exactly what Fisher is saying. He's saying we should report the p-value, and maybe we use 0.05 as a practical cutoff, but it really depends on what we're looking at. But people are going to take this word as gospel, and 0.05 is going to be the cutoff for psychology. More about which soon. So calculating the p-value is easy enough for me to show you when we are showing this T experiment, but it's going to be difficult to do for our real studies. All right, it's going to require some intense math. All right, so what happens if we make this a little bit more complicated? Instead of having 3 trials, we have thousands of trials. Instead of having a discrete variable with 2 different outcomes, how about we have 4 different outcomes? How about we have a continuous variable? All right, what happens if we don't know what the population mean and population standard deviation are for when we randomly sample things from that population mean and standard deviation? Calculating this p-value is going to be complicated. It's going to require calculus, and ain't nobody got time for that. Okay, we don't have time to do that. We don't have the chops to do that, and it's a waste of our time. So we're going to get SPSS to calculate the p-values for us. Okay, so but I just want you to know conceptually what's going on with this p-value. Okay, the p-value is the probability that we would have obtained these results from our study just due to chance. All right, results as extreme as the one that we see, or more extreme than the results that we see. All right, that's what a p-value is. I want you to wrap your mind around that. Okay. We will stop this video right here, and we will finish null hypothesis significance testing in the next video. Thank you, and I will see you in a bit.